This is a talk about interfaces. So I'm going to start by showing you a couple of examples of semantic interfaces, which are the interfaces we have today. So here you see a snippet of the Java socket interface, specifically the connect method. And what this interface does is it tells you the arguments to the method, what the method returns, and gives you an English language description of what the method does. Now, most importantly, this method only contains the information that a socket user needs to know. Everything else is abstracted away. And it's really this abstraction which is what makes this interface so useful, because now we can use this socket without wondering about how it's actually implemented. Now, here's a second interface, which is in the form of a program. And really, the English language description in the previous interface has been replaced with a set of pre- and post conditions. Now, this interface is slightly more hard to read, but it allows users to reason more precisely about what the code does. Now, we've all seen interfaces like these, and they're really indispensable if you want to build large and complex systems. And any good interface must provide a balancing act between simplicity and precision. And by simplicity, I mean two things. One is conciseness, so how small the interface is with respect to the actual underlying implementation. And two is accessibility, so how easy it is for an ordinary developer to actually understand the interface. So in this work, the question that we ask is, can there exist such a thing as a performance interface? So is it possible to have an interface that only describes the performance properties of a piece of code that a user needs to know and abstracts away everything else? And is it possible to keep this interface concise and accessible when performance typically ends up depending on low-level implementation details? And in this talk, I will argue that it is possible. We can have performance interfaces, at least for network functions or NFs. Further, I will argue that having such simple and precise performance interfaces allows NF developers and operators to do things that they couldn't do before. So for instance, once you have a performance interface, it becomes very easy to identify regressions and bugs that you might introduce or diagnose the root cause of in-production performance anomalies. So if there is one thing that you take away from this talk, I want it to be that we can have performance interfaces that summarize NF latency in a simple and precise manner, just like semantic interfaces summarize functionality today. So here's the outline for the rest of the talk. I will start by introducing our proposal for what performance interfaces look like. Then I will describe a couple of use cases showing how developers and operators can actually use these interfaces. I will then talk a little bit about our tool, which extracts performance interfaces from NF code, and finish with a few highlights from our evaluation. So what do performance interfaces actually look like? So on the right of this slide, you see a performance interface for a NAT written using DPDK. Don't try to read it now. I will walk you through the whole thing. Now, first and foremost, the performance interface is a program. And this program takes in the same inputs as the underlying system, and it returns the performance of the underlying system. So in this example, the performance interface takes as input a packet, just like the NAT, and returns the performance of the NAT. Now, most importantly, this interface does not tell you anything about how the NAT actually processes the packet, because the functionality of the NAT is not its concern. Now, what do I mean when I say returns the performance of the NAT? In this work, we focused on latency as opposed to throughput, and we quantify latency in terms of three metrics: the number of x86 instructions, the number of x86 memory operations, and the CPU cycles. Now, each of these metrics serves a different purpose. The instructions in the memory operations are really intrinsic to the code itself. So they help developers reason about the code. And on the other hand, CPU cycles is really what we care about, because that ultimately affects user experience. So in this portion of the talk, I'm going to focus on x86 instructions for ease of illustration. But I will come back to CPU cycles when I describe how we extract interfaces from code and also in our evaluation. So now we have a program that takes as input a packet and is going to tell you the latency incurred while processing this packet. But the latency does not depend only on the input packet. It also depends on state built up by previous packets, which can vary a lot depending on the workload. So to ensure that the performance interface is accurate, even in the presence of dynamic NF state, we have the interface return performance as formulae as opposed to concrete values. And these formulae have free variables that we call PCVs, or performance critical variables. And what these really do is capture the effect of state on NF latency. Now, more precisely, the set of PCVs is really the abstract state that one needs to reason formally about performance. So in this example, one of the PCVs is C, the number of collisions in the flow table that the NAT maintains, because when you look up a flow, the latency is naturally going to depend on the number of collisions you encounter. So now we have these formulae in the interface, but we still end up having a number of low-level implementation details that we need to get rid of. So to do so, we introduce the notion of a performance resolution, which really tells you the granularity at which the interface describes performance. The idea behind the performance resolution is very simple. Users typically don't care about cycle-accurate performance predictions. They're willing to tolerate a certain level of variability. And so what the performance interface really is this incredible tool that developers have to vary the level of abstraction that the interface provides. Because given a resolution, the interface will eliminate all implementation details that do not matter at that resolution. So in this example, the resolution is 1, which is the finest granularity. But if we increase it slightly, let's say to 10 instructions, we see that the interface becomes a lot simpler because it can discard a whole number of implementation details. So the interface that I just described with a resolution and performance formulae is what we call a general case interface, because it can describe the performance of the NAT for arbitrary workloads because of the performance formulae. Now, let's take a look at how this interface does with respect to the design requirements I put up earlier. Now, this interface is precise because of the formulae. It's also concise because it's much smaller than the implementation. But is it accessible? And it turns out that it's not really accessible, because while the formulae with PCVs are easy to understand for someone who actually wrote the code, they're fairly difficult to understand for someone who just wants to use the code, because they reveal a bunch of implementation details about the underlying state store. And so to address this final challenge, we introduced the notion of deployment-specific interfaces. And the idea here is that someone who wants to use the NAT doesn't necessarily care about its performance in the general case. They care about its performance in their deployment, so for their workload and for their hardware. And so what this interface does is really instantiate the general case interface with distributions specific to a particular deployment. And by doing that, it's able to get rid of the PCVs and return performance as concrete statistics. So in this example, the interface returns the 99th percentile latency, and it returns them as concrete numbers. So to summarize, a performance interface is a program that takes as inputs the same inputs as the underlying system and returns the latency. It has a resolution which specifies the granularity at which it describes performance. I told you about two kinds of interfaces: a general case interface, which describes performance as formulae, and a deployment-specific interface, which describes latency as concrete statistics, but specific to a deployment. So that was what performance interfaces look like. Now I will describe a couple of use cases which show you what you can do with performance interfaces. So the most straightforward use of performance interfaces is to use them to identify performance regressions or bugs that a developer may introduce. And to do this, we took Katerina, which is a load balancer from Facebook, and extracted an interface before and after each commit. And we compared the maximum processing latency, which for Katerina is the latency for processing new TCP flows. And the table displays the results. Now, the point of this slide is not to tell you that these regressions are bad or the developers weren't aware of them. It's to tell you that developers can now have this information at their fingertips by using performance interfaces, whereas previously they would end up having to write a bunch of tests and hope that they provide good enough coverage. For operators, performance interfaces can help them conduct precise root cause diagnosis for in-production anomalies. And the reason for this is because when you have performance formulae expressed as a function of PCVs, you will typically end up having a strong correlation between observed performance anomalies and one of the performance formulae. So for instance, you might encounter anomalies due to a number of hash collisions, or due to high churn, or due to the flow table not fitting in on a particular x86 server. We encountered all of these while doing this work, and in each case, the performance interface was able to precisely pinpoint the root cause. So at this point, I've told you what performance interfaces look like and how you can use them. Let's now take a look at how we actually extract them from NF code. So to extract these performance interfaces, we built a tool we call PIX, which takes as input an NF written in C and spits out performance interfaces as Python programs. Now, before telling you how PIX works, I'll talk a little bit about its limitations. First, to be precise, PIX relies on exhaustive symbolic execution, and so it requires that the NF code is amenable to it. This means that the code must be single-threaded, it must have statically computable loop bounds, and must store its state in cleanly separated state stores. Second, the performance interfaces extracted by PIX do not account for performance interference. We think that performance interference due to collocated programs is an orthogonal problem that needs to be solved by purpose-built tools. The idea of an interface is to tell you the performance of your code. Lastly, our current prototype does not reason about queuing latency. It only reasons about processing latency. This is because when you want to reason about queuing latency, you need to reason about more than one input at a time, which is something that exhaustive symbolic execution cannot do yet. So that said, here's a quick overview of PIX. PIX comprises a front end and a back end. We envision the back end being run by the NF developers when they push code or release code. And it takes as input the NF source in C and spits out general case interfaces. We envision the front end being run by NF operators. And what this front end does is it instantiates the general case interface to extract deployment-specific interfaces for each deployment. Now, one crucial aspect here is that the front end does not require the NF source anymore. It just requires the NF binary and the extracted general case interface. So now the front end is fairly simple because it only instantiates the general case interface with distributions. So I'm going to focus on the back end here. So here is an overview of the PIX backend. It contains 4 steps that I will now outline. So the first step is a tool called Bolt that we built a couple of years ago. And what this tool does is it exhaustively symbolically executes the NF code to extract all paths. And in doing so, it plugs in pre-computed contracts for the data structures that the NF uses. Now, we can pre-compute the contracts for the data structures because if you look at almost any NF framework, the NFs typically end up using a bunch of similar data structures and simply reusing them. So we can pre-compute the performance contracts or interfaces for these data structures once and simply reuse them across interfaces, across NFs. The output of this stage is basically the number of instructions and memory operations per execution path through the NF. The next stage is the NF hardware model. And the idea here is fairly simple. It's that once you eliminate performance interference, your primary source of variability for an NF comes from the memory hierarchy. So what this step does is it utilizes state analysis to identify potential LLC miss sites. And whenever it encounters such a site, it adds a PCV saying, here's a miss and a free variable, which is called LLC miss latency, which the PIX front end then instantiates for each hardware platform. The next 2 steps are fairly simple. The third step translates SMT queries into human-readable Python expressions. And the last step basically takes in a resolution and eliminates details that are irrelevant at that resolution. The end result of all these steps is a general case interface, which expresses performance as a formula. Finally, I'll zip through a few results from our evaluation. So we used PIX to extract performance interfaces for 12 NFs written using DPDK and eBPF's express data paths. These are arguably the 2 most popular ways to develop NFs today. 3 of the NFs we extracted interfaces for are actively used in production. Katerina is a load balancer from Facebook. Natasha is a NAT used at Scaleaway. And we also extracted an interface for the filter used by Cilium. We evaluated the extracted interfaces on 3 criteria. 1, how accurate they were. Second, how long it took to extract them. And finally, how simple they were compared against the underlying implementation. Now, in the interest of time, I won't be able to go in detail into the simplicity results. But I can tell you that the interfaces are typically 2 to 3 orders of magnitude simpler than the underlying implementations. So let's take a look at accuracy first. Now, the first question is whether you can actually extract interfaces that are accurate across different deployments. And so to do this, we extracted interfaces for all the NFs across 4 deployments, which is a cross product between 2 workloads, 1 typical and 1 adversarial, and 2 hardware platforms, 1 fairly old Intel Sandy Bridge server and one new AMD EPYC. And what's interesting to note here is that despite the absolute NF latency varying by up to 3x, the prediction error remains fairly stable at around about 8 to 10%, which tells us that PIX extracted interfaces can accurately adapt to different deployments. A second measure of accuracy was the robustness across different latency percentiles. And here on this graph, you see the prediction accuracy for all 4 deployments at the 50th, the 90th, and the 99th percentile. So we see that up to the 90th and really the 95th percentile, the prediction accuracy is once again stable and between 8 to 10%. But this increases at the tail, where it goes to around 15 to 25%. The reason for this increased inaccuracy at the tail is because our simple hardware model of only considering LLC misses becomes invalid at the tail, where a bunch of other hardware details start mattering. Finally, here is the time required to extract the performance interfaces. For most NFs, it takes PIX less than 5 minutes to extract the interface. For the more complex ones used in production, it takes between 20 and 30 minutes and topping out at around 32 minutes for Katerina. Based on this, we conclude that it should be feasible to incorporate extracting performance interfaces as part of the regular NF development process. So, to summarize, today I've told you about performance interfaces for NFs, and what I want you to take away is that performance interfaces can summarize NF latency in a simple and precise manner, just like semantic interfaces summarize functionality today. The code for PIX, the paper, and the NFs we extracted interfaces for are all available at the link. Thank you for your attention, and I'm happy to take questions.